So today we're going to continue with project planning and scheduling, but we're going to look at the other learning intentions. So we're going to talk about what forward and backward scanning is, and some terminology that we'll have to get familiar with is earliest starting time, latest starting time, and critical path. Okay, and we'll also have to look at minimum time and float times and non-critical activities. So this terminology must mean something to you by the end of it, and when used in an exam question, you'll be able to decipher exactly what the exam stimulus wants. So we're talking about project planning, all right? So there's multiple activities that need to be done at certain times, and it's used in all industries, and something that can save you a lot of time and money if done correctly. Now, the precedent tables that we've been looking at in the 12A didn't have any weights on their activity. So now we're adding, this is like a weighted graph now, isn't it? Or network. So this is usually time or money or some sort of resource length that allows us to make sure that we can work out the minimum weighted network or something similar that we've done before, even in chapter 11 with minimum spanning trees. So we should be used to activities or edges having some sort of weight, okay? And so here we're going to use the idea of immediate predecessors and weights, and we're going to combine them to have a look at these two things called critical activities and float times. So let's consider this situation here where we have activity A and activity B can be done at the same time as activity C is being done. In this case, we're going to be talking mainly time. So this is 5 hours, this is 3 hours, okay, and this is 6 hours. So before we can start that next activity here, we have to complete A and then B. All right, so the minimum time that the earliest starting time that we could start this activity going across in this direction, probably called activity D, would be 8 hours. However, C here only takes 6. So different people look at this in different ways, but you can use a table. So here's activity A followed immediately by activity B, total of 8 hours, each square looking at 8 hours. C has a couple of different options. It can start straight away and have 2 hours slack time at the end. It can wait an hour, do the activity for 6 and have an hour slack time at the end. Or it can have the 2 slack hours at the start and then complete it. So these slack times here are called float times. Okay. Now in this particular simple network, AB is the critical path. Okay. Critical paths have no float time. So A into B, all right, has no slack time, no float time, and therefore is the critical path. So critical path analysis is basically looking at the path that cannot, be delayed. So if you're choosing which activity to run at first, or if your resources are limited and you have to determine which project gets a certain number of resources, whatever you want to do is you always want to give the critical path the preference, all right? Because if you delay the critical path, you will affect the overall completion time. If you don't, so like if you affect another activity, like in activity C that we just looked at, if we do that and we affect it by 1 or 2 hours because of resource delay, it's not going to affect the overall finishing time because it had some slack there. Okay, so now these next steps here are for your reference. They're on the slides, they're also in your textbook. We're going to do a thing called forward scanning to identify earliest starting times, and then we're going to do backward scanning to identify latest finishing times. And so we'll look at this in an example situation. Now, when you're researching online, this is sometimes what you'll see. Okay, we continue this to be the activity and this to be the duration, okay, or the weight. And then in the boxes up to the top right, okay, would be the earliest starting time that's listed, and the bottom right would be latest finishing times. The book does it slightly different, and we'll get used to the way that the book does it. Okay, so the book does this. For every vertex, okay, you have a early starting time and a latest finishing time. All right, so the one on the left in yellow is the earliest starting time, and the one in blue is the latest finishing time. So for each vertex, you can either draw these boxes, or I do it with brackets and list all of the different ones, which we'll start to do now. Okay. So this is the activity that we got here. Remember, the dummy network means that C is an immediate predecessor to F. That's just a bit of revision. Okay, so we put a 0 in the starting box, yeah, and this means the start of the whole project is at time 0. Then what we do is we talk about forward scanning. Okay, now we're starting here at 0. If this takes 8 hours and the earliest starting time is 0 for this particular vertex, then the earliest starting time for that next activity, activity C, will be at 8. All right, or any activity coming off that vertex will be earliest starting time is 8. That takes 1 hour. Okay, so then the earliest starting time of either E or F is going to be at 9. Okay, now because we're now linking back up down here, we also got to consider this situation. So we go 6 and then 2. Okay, so this here is 6, but when we come to this situation, this path here would have taken 8 hours. This path here would have taken 9 hours. We can't do F until we've done C. So what do we put down here? We actually put down 9, okay? The minimum or the earliest starting time is 9. Even though this one will be finished after 8 hours, it can't start until C is finished. So we'd put 9 in this situation here. Now we have 9 there to here will be 12, or we can go from 9, 1 will be finished at 11. Now we've always got to take the maximum. This is the restricting number here, right? So we can't do G until we've done E, and E won't be finished until 12 hours. So we'll put a 12 in here. Okay, I'll just skip to the next slide because that's for you. This is showing us. We'll put a 12 in here, and then we finish this off and we go 2, okay, and then 1 more, and a bit too much. So we end up with this, and that's the end of forward scanning. Okay, so you've got to consider the different options, all right, and you always take the maximum time as your minimum or earliest starting time, because it's the limiting factor. So we have to really consider those immediate predecessors. So once you've done forward scanning, okay, what this really represents here, okay, is the earliest finishing time for the project. All right, the project can't be completed in any time less than that. Now we're going to do backwards scanning and look at the individual activities to determine any float times, okay, and to determine when they are, what's the latest finishing time for those particular ones. And that will allow us to determine what's the critical path, okay, and the float time, as I just said before, for each of these activities. So what we do is we start at the end vertex and we put a 15 in here. Now if we go back, this will be 14, meaning that the latest finishing time for G will be 14 in order for it to get to 15. Now same thing here, the latest finishing time for this activity F and E will be 12 in order to make that time 15 there. But this is where it gets a little bit difficult, so it splits now. So if this is 12, the latest finishing time for for D and for C here is actually 11. All right, it finishes at 11, okay, then it can still get there to 12, and we see a difference here between 9 and 11, and that's going to help us determine float time in a minute. Looking back in the opposite direction though, this one here, okay, 12 goes back 3, that remains 9, so we get 9, 9 here, yeah, and then we can work back 8, 0, and what we'll see is that all of the ones on the top 15, 15, 14, 14, 12, 12. We have the earliest starting time and the latest finishing time. They're actually going to equal each other. Whoops. Preview. A bit of like this. Okay, so once they're all going to equal each other, that will become our critical path with no float time. But what about the ones down here? So the activity F could start at 10, all right, and it would still be finished by 12. Or it could start at 11 hours and still be finished by 12. So this is its latest start time, really. Okay, so this activity here will be finished. All right, we can choose when we're going to start F in order to get there by 12. Same thing back here. In order to get to here by 11, okay, we could finish this activity at 9, which means that it has 3 hours it can choose to actually when it starts here. So if it started, okay, at, let's say 1 hour, then you'd go 6, yeah, and then that would then become, oh well, this is not 6, sorry, 7, and then this one would become 9. It would actually start there at 9, okay, but if that didn't happen, all right, what would happen then? If this started at 2 hours, then it'd be finished at 8, then 10, and then 11. We'd still make it in time for A, C, and E to be finished. Or we could start at 3 hours, and then we could finish here at 9, then we could finish here at 11, and then we can still get there by 12. And so these are your like limits for like the latest finishing or starting time for that particular vertex or that particular activity that comes after that. So how do we determine this latest starting time? That's kind of what I was just talking about there. All right, is we take the latest finishing time and we subtract the length of the activity. So for in this example here, we have an activity of length 6. All right, the latest finishing time is 9. Take that away, we get 3 days, okay, or 3 hours, depending on what the time is there. Okay, and so it doesn't matter when you start that in terms of delaying the end of project. It's just what we call slack time or float time. I gave to you. So how do we calculate this float time? We take the latest starting time and we minus the earliest starting time. So 3 minus 0, 7 minus 6, 11 minus 9. That's a mistake there. That should be 2. The textbook, always good for a couple of mistakes. Before, it says latest start time minus earliest start time. Now, so what I've done here, I've actually added a column to the one in the textbook. All right, and so when we look at our table here, what we get is we can have these earliest starting times, latest finishing times, okay, and that can be used to work out our latest starting times, yeah. And once we've done that, what we really do is in the slide, so latest start time minus earliest start time gives us our float time. Latest start time, earliest start time gives us our float time. Now these zeros, just like when we're doing the Hungarian algorithm, they're the important ones, okay? That actually, anything with a 0 in it means that it can't be delayed without affecting the final finish time, which then becomes our critical path, the one that we should follow. Path analysis. And so in this case here, as I said before, we're going up and we're working those out. Now another way that we can do float times quite easily here is we can say that is 0, that is 0, that is 0. Here we have 2-hour float time. Here we have a 3-hour float time. And all the ones at the top, which have the same numbers, have a 0 float time. And that will help us work out that this is our critical path. Okay, so there's a couple of different ways to work through it. I like this graphical version more than the actual table of values, but everyone is different, and so you need to choose the one that helps you. So let's have a look at the critical worked examples now. So in this particular case here, instead of boxes are sometimes a little bit difficult. We can just put little brackets, okay? So we're going to have 2 numbers. The first one's going to be the earliest start time, and then the other one's going to be the latest start time. So we start there at 0, 0, and what we do is we can do a bit of forward scanning now. So we follow this along. Okay, when we get here, we see that, oops, I'm just going to choose my red pen again. We see that this is going to have an earlier start time, which is going to be 3. And then as we follow this down here, actually I'm just going to go through and put my little brackets in for each of them, so I know my brackets are. So each vertex will get a set of brackets, and that one we don't need. Okay, so if I follow here, I go 3, okay, and then I come back here, I'll be finished in 7, okay, and I need to do D before I do F. Okay, if I just go this way, I'll be finished at the end of 5. Okay, and so that we're talking weeks now, 5 weeks. But I can't start F until I've done D, and I can't start D until I've done A. So what's going to go in here is going to be my earliest start time, which is 7. Okay. Now, the bottom one is quite easy. As I follow this down, I get 12, which is easy. And then up here, I have to consider both options. I have to consider this option, but I also have to consider this option. And now here, I also have to consider A, then E, and then also A, D, F, and then also, A, B, F. So I have to consider quite a few things in that top one. So if I go up the top, I got A and then E, that's 10 hours. If I go A, D is 7 and then 5, that's going to be 12 hours, okay? So this here is going to have a 12 because I have to do A before I do D, which takes 7 hours. And then I have to do D before I do F, which is another 5 on that 7, so that's 12. So even if I went this way, if I went A then E, okay, I'm going to have a float time of 2 hours along here because it doesn't matter when I start. Within that 2 hours, I'm still going to get there before I finish A, D, and F. So that's the type of thinking that we have to have. Now we're considering from 12 here, 6 will be finished at 18. That's the earliest time we can be finished. At the top there is 18. If I go this way, I'll be finished in 14. So realistically, this has a float time then of 18 minus 14, which is 4 hours. So we can choose when we start that one without delaying the project. So we'll put our 18 in here, okay, and then when it's to finish, we put another 18. Now we can go backtracking, okay. So we've just finished forward scanning, tick, okay, and the minimum time it will take to complete this project is 18 weeks. So we've answered question A. Complete the backward scanning process. So backwards along this line, that's the latest finishing time is 18. If this takes 2, all right, down in this one here, we're going to have 16. All right, now, then at the top, 18 minus 6 is going to be 12. So you can see straight away that that's part of the critical path. And then 12 take away 5 is also 7. But 12 take away 7 at the top here, all right, this one here is going to have some float time that we're going to get used to in a minute. But we have to consider this one has 2 points coming from it, and we have to consider the critical path. So that's going to be 7, and then we're going to take away here 4, so that's also going to be 3. All right, and so we can kind of see the float times already. That's going to be our critical path. It's going to be anytime this is matching. So it's going to go A to D to F to G. That's our critical path analysis. We don't want to delay any of those particular ones there. So tick. What is the earliest starting time for E is what they're asking for. Well, oops, I shouldn't circle that. If this here is our latest starting time, then minus the activity time, can you see that that's going to be at 5 hours? So, earliest starting time's 3, so we can start at 3, but the latest starting time is actually 5 for this activity. All right. So the earliest starting time, yes, it can get done after 3 hours, yes, or 3 weeks, sorry. What is the latest starting time? That's the end one here, which is the latest finishing time minus the activity, which is going to be 5. Okay, so that means that this activity here has a float time of 2. Identify the critical path. Well, as I said before, that's this critical path there, and you would describe that as A, D, F, G. Okay, and the person responsible for completing activity E falls sick 3 weeks into the project. If he will be away from work for 2 weeks, will this cause the entire project to be delayed? No, it won't, because it has a float time of 2, which is what we kind of spoken about before. Okay, so we got our critical path analysis. We do forward scanning, considering the minimum time to get to a specific one, considering the predecessors, and then we finish it off and go backward scanning to work out the latest starting time. Let's have a look at a bigger project here, and this will take a while. So basically, we got Linda is building a new house and has decided to manage the project herself. She's decided on these following activities. Yep, and she's got some advice, and this is the times in days it takes for each of the activities. It wants to construct an activity network for this project. So we've done this before. We have to consider the predecessors, and let's not try and be super neat from the get-go, because when you're doing these, you'll find the problems and you might have to reconnect. So either draw it in pencil, okay, or have a little chicken scratch and then redo it at the end. So we have activity A, all right, and that's going to take 5 days, and that is preparing the site. After you've prepared the site, they can construct frame and roof, okay, but you can't do that until you've prepared the site. So here's activity B, and that's going to take 25 days. And then C is preparing the floor, also has to have the site prepared first. So we go C here, and that's only going to take 3 days to prepare the floor. The landscaping gardens apparently can't be done until they've constructed the frame and roof. I'm not sure why that is the case, but I'll believe them. So we go D, and that is 10. And then down here, what we have is installing plants and lawn. Well, yes, you can't install the plants and lawn, okay, until you've landscaped your gardens. So that's only 3 days, and it comes after D. Installing electrical work. Yep, that has to become after B. And installing plumbing comes after B and C. So anytime we see a double up when they're not just by themselves, we know that we have ourselves a dummy. Okay, so B and C lead into G. And G was going to take 6 days. Let's go back to installing electrical work, which is F. Okay, now F comes after B, and F and G have to combine to finish off the house, which is H. So that's 5, H is 5, but what did we say F was? F was installing electrical work, all right, and that can't be done until you've landscaped the gardens. So, and that took 4 days. All right, I think that's our activity network now. So what we've got to look for is apply the full. And as I said, this could get messy and you might have to redraw it. I'm just scanning back through to make sure that I've ticked off all of those, which I think I have. Now it says construct and apply the forward scanning technique to determine the shortest time in which Linda can expect the completion of her house. So I'm going to change to red here so I can discriminate between. So we've got to start at 0, 0. Okay, and then we get in here, and at this particular vertex here, A took 5, so that's the minimum time. Now to get up to this vertex to B, or not vertex B, B is an activity, we're looking at 30. Okay, and now to get to C down here, well that's going to be, if I go this way, it's going to take 8. weeks. If I go this way, it takes 30 weeks. But you can't do G until you've done A and B. So this becomes our limiting factor at the top there. And so this earliest starting time for G is actually going to be 30. That's a lot of slack time going that way. Okay, so that's 30. This up here will be 40. All right, takes 10. Now if we go the long way, because we have to consider the long way, we go A, B, there, that would be 34. Or if we go this way, A, B, G, that's going to be 36. All right, so we have to consider the maximum one. So this one down here is 36. Now if we go to the top from here to here, it's going to be 43. If we go from here, we go from 36 to H, which is going to be 41. We have to consider the maximum, which gives us 43. Okay, so we throw a 43 into here. Now we backtrack 43 to 5. Well, that's going to give us 38. So we've got some float time going that way. Back up here is going to be 40. Okay, and then back down here is also going to be 40. And then back down here is going to be 5. All right, and that obviously is 0, 0. And so we can backtrack and just fill this next one off. We've got 38, and this takes 6 hours. So we could actually start this G at 32. Okay, that's our latest starting time. So we've got a lot of slack there. Now, when we're going, the question is asking, when we're going forward scanning to determine the minimum time to completion of a house, we look at the critical path. So these are the ones, oh, that's a mistake. Should be 30. You would have stopped me in class if I was doing that. So these are the ones where they're the same. So the critical path is A, B, D, E. That's the critical path, and the minimum time takes 43 weeks to build a house. Now construct a table that shows earliest starting time, latest finishing time, latest starting time, and float for each activity. Okay, I might just erase. No, I won't erase it, I'll just slide it in here. Quite a few activities going on. It's not just the activities, it's actually, I'll make that a bit smaller, that'll be better. So let's have our activities down here. That's our activities. And then underneath here, we're going to have our latest starting times, float times, and the lot. And you would be using a ruler and doing this a lot neater than me freehanding it on an iPad. So we have our earliest starting times. We have our latest starting times. We have our latest finishing times. And we have our float times. And we should actually have in there as well our activity times. So I will erase that now. Oops. And I'll redraw it underneath it. So it's 43, 43. All right, that's going to be your activity time, and that's going to be your activity. Okay, so activity A, B, C, D, E, F, G, H. Activity time, what have we got here? We got 5, we got 25, I'm just copying off this table up here, 3, 10, 3, 4, 6, and 5. Okay, and so the earliest starting times that we went through and calculated with our forward scanning, okay, is 5. B was 30. Sorry. that's back off a little bit. Where's my eraser? A actually starts at 0, B starts at 5. Okay, so we're looking here for the start of A. C is also 5. D is 30. F is 30 as well, all coming from the same vertex. And that's a dummy activity. So E here comes from this vertex, so it has a start time of 40, earliest start time of 40. And G has an earliest start time of 30. And H has an earliest start time of 36. So we look at the vertex to determine those. Okay, the latest start time, right, is what we determined with our backward scanning. Is latest finishing time. Actually, latest finishing time is what we determined with that there. So we're looking here. E and H both have a latest finishing time of 43. So, and then from 43 back, okay, we're going to look at this vertex, which is got F and G finishing at that particular one, and they have the latest finishing time at 38. So this is 38. Now C, okay, has a latest finishing time of 32, and D has a latest finishing time of 40, B 30, A 5, and H down here, I should have already said 43. So now we have our latest finishing times. We have to go back and work out our latest starting times. Our latest starting times are just looking at, well, if this is the latest finishing time down this column and the activity takes this long, well, when's the actual starting time that we can start? And so in this case here, we're just going to go 5, subtract 5, which is 0. 30, subtract 25 is 5. 32, subtract 3, 29. 40, subtract 10, 30. You get the picture. So now we have our latest starting times and our latest finishing times. And one of the reasons I did the table a little bit differently to the book is these are ones we're sort of comparing now here. We have the earliest starting time and the latest starting time. And this will help us determine our float times a little bit quicker. All right. So the float time is the difference between those. What's the earliest you can start and what's the latest you can start? So we're taking our latest starting time, subtracting our early starting time. We get 0 here, 0 here, 24 here. That's 29, take 5. 0 here, 0 here. We get a float time of 4 for activity F. 2 here. And H, 43, 38, take 36, which is 2. All right, so these are our float times. And you notice straight away that these float times, the zeros are the critical path. A, B, D, E, that's our critical path, and they've all got them, zeros next to them. So, have we answered the question? Construct a table, done that. Which of the activities will cause a delay in the entire project if they take longer than expected? They're the critical ones. There's your A, B, D, and E. Okay, write down the critical path of this project, A, B, D, E. If the electrical work takes 2 days longer than expected, will this have an effect on the overall project? So electrical work is F. We go to F. It has a float time of 4 weeks. Or is it weeks? Oh no, it's days. Okay, so 2 days longer. So we got 4 days. So we have a float time of 4 days. A 2-day delay won't affect the finishing time at all. Assume that all other activities have no delay. What is the maximum delay possible for the floor preparation so the whole project is not delayed? Floor preparation is activity C. All right, that's 24 hours, or 24 days, sorry. 24 days has a float time, so the answer for that one is 24. So quite a few steps, but if we go back and we just